Perfect. Okay, so let me do this iPad thing and let me share with you. So 1 second. Okay, so can you guys see the screen?
Yeah.
All right, folks, good. Okay, so I have more people from the waiting room, so let me get this started. So um, I want to show you two figures here mainly. Okay, there are a top figure and on the T-beam, and there's another figure here on the irregular section. So let's start from here. So this is a typical T-beam, cross section of T-beam. Okay, now I want you to pay attention that you have two components in this cross section, right? So in case it's not clear enough for you, in case this is not clear enough for you, let me draw the 3D drawing. Okay, so let me move this one a little bit lower. So this is the cross section you typically see from a joist or from a slab beam or like just a T-beam integrated section. What really looks like in the 3D view, it looks like something like this. So I'm just trying to draw in a corner. So here, and then I have a L, they call it spandrel beam. This is L-shaped, or some people call it spandrel. Okay, and then I have a T-beam like this. Okay, and something like this, and so on and so forth. Okay, all right. So the section you're seeing here, right, on the top is where I make a stop right here. Okay, and then make a stop right here. So this is the T, this is the L on the left. Okay, so why I bring this picture up, because in the reality, when we talk about this section design, we normally ask you guys to do the design based on the effective width, right? So that effective width is in the flange, but this effective width turned out is a function of the beam width, which is the BW right here. Okay, so on the left, it is a equation for the BE effective width for the L shape. So this is smaller than equal, right? Smaller than equal, right? Meaning you take the smallest, right? You take the smallest value of V3, right? So what are these three? First is BW, which is the web, plus SW divided by 2. I'm going to use red so you can see it. Follow me. SW divided by 2. What is SW, right? What is SW? Now, here says SW is a clear transverse span between webs. Clear transverse span between webs. That means it's the clear span distance between the inside the wall to the inside of the wall, right? So this whole thing here is called SW. Okay, this whole thing here is called SW. All right, clear span. Okay, clear span, transverse. All right, and then the second one is BW plus a 6 HF, where HF is the height of the slab or the flange, right? Height of the flange. And the last is BW plus LN divided by 12. Ln divided by 12. Now this, you don't see it, right? Ln meaning clear span of the longitudinal direction, clear span the longitudinal direction, right? So that means Ln is this direction. Ln is this direction. Now we typically give you this, okay? Typically give you this, and you can see this from the homework. We typically give you this. Okay, so this is on the L shape. This is on the L shape. So you pick the lowest number of the three. You pick the smallest value of these three. For the T-beam, it's a little bit different, right? For the T-beam, you have two sides now. You have two sides now, right? So have BW plus 2 multiply SW divided by 2. SW divided by 2. Right? So SW divided by 2 is the clear span, transverse direction, right? Half of that. Or BW plus a 2 times of HF, where HF is the height of the flange, or BW plus a 2 times of Ln. Again, Ln is the clear span length in the longitudinal direction divided by 8. Okay, so that is how you determine the effective beam width. Effective beam width. Now, back then when we talk about the T-beam, we didn't show you guys this detail. So today you can see it here, right? You can see it here. So in short, for your homework and for future exam, all you have to remember is these equations. This one, and let me just clear it out, and this one. So on the left, this is for L shape. Okay, on the right, this is for T shape. Okay, and only thing critical that you have to be able to differentiate is the Ln is longitudinal span length and SW is the transverse span length. They're different. They're different. Okay. All right. Any questions on this, folks? Are we good on this? Okay. So if this is the case, let's open up the homework, right? Let's open up the homework. Let's talk about a little bit. Talk about a little bit. So where are we at? Hold on 1 second. Teaching homework. Where are we at? Here. For design. Hole number 6. See it. Okay, this should be it. Okay, hold on. This is modified, but that will work. Okay, let me stop share, reshare you this screen here. So this is the homework. This is homework. Well, I label here 4, but in your version 3, that's the last problem you have. So you see that we have a T-beam. There's no L-shaped beam for this one, right? So naturally, you use the equation for T-beam. And now you have a beam span length of 4.5 plus 4.59 feet, but that's not clear. That's not clear, okay? All you have to do is figure out the pure or the clear span length from inside of the wall to the inside of the wall, right? So you have to subtract this span length, right? Subtract the span length from, well, remove the beam width BW from it, okay? Okay, so this is how we find out the transfer span length, okay, for the homework. And the rest is a simple process as we did for T-beam, okay, as we did for T-beam. So coming back to share the screen again. So for T-beam, we talk about this, right? There are two components. Right? So if I draw the T-beam here, blue curve, blue color here, and I have two parts. I have the little bit extra, okay, this is part 1, and I also have the middle portion, part 2, okay. So when you calculate, you first have to determine A. You have to determine A first, right? So when your A is smaller than the flange height, HF, you can treat it as rectangular section. But when your A is bigger than HF, as the case showing here, you have to do the separate part. You have to do the separate part. Okay. All right. So this is the T-beam. Okay. This is for the T-beam. Okay. Any questions on the T-beam so far? Any questions? If you still have trouble solve the homework, right now is good timing. Any questions on this? Okay. All right. Okay. So let's move on. For the irregular section, right? For the irregular section, I show a illustration for a triangle section. Why that is, I just want to warm us up again, repeating what we have talked about before, how to find the compressive zone for an irregular section, right? So you can see it has a shaded area, right? So essentially, we still don't know the effective compressive zone A. What we do is we let T equal to ASFY. T equal to ASFY. We know the bar. Typically, we know the bar. Okay. For the irregular section, we probably won't ask you to do any design problem in the exam. Haven't determined it yet, but most likely will not. But so most likely it's going to be analysis, right? For the analysis, you will find the tension first using ASFY. Once that is settled, you let it equal to the area of compression, which is AC. Okay. Now in this triangular shape, right, the area will equal to, of course, 0.85 F prime C. That's the compressive stress, right? Compressive stress, and multiplied by the area, right? Multiplied by the area, right? What is the area? So you think about this is A beta 1C, right? So this compressive block is A squared divided by 2 because it's equilateral triangle. And A equal to basically 0.85 prime C, just write it down. And this is beta 1C squared and divided by 2. So all you have to do is solve for C to get your compressive zone, right? And once you solve for C, things are just easy, right? You can find the central of this area, central of this triangle area. That is where the compression force is sitting at, right? 2/3 of A, 2/3 of A, right? 2/3 of A. And then you can use the moment equal to tension or ASFY multiplied by the depth minus 2/3 of A. 2/3 of A. Okay, so this is JD. Okay, this is JD. Okay, so that's how you do the triangle section. Well, you probably say, Bob, it has nothing to do with our homework, right? Our homework is not like that. Our homework is a rectangular section with an opening here, right? With an opening here. This is our problem. This is different from triangle, right? So it's complicated. And besides that, you know that we have 3 number 10 bars, right? So this is 3 number 10 bars. Okay, and then the problem is to find out the moment capacity, right? So what do you do? Now, all you can think of right now is first we need to find ASFY, right? So being 3 number 10 bars and number 10 bars is 3 area 1.27 inch squared. And I know the problem is 75 KSI, but I'm just going to assume for now, Fy equal to 60 KSI just to ease my calculation up, okay? So this 60 KSI. So that's my total tension. Right? So with this, I'm supposed to find the compression force. So ASFY equal to 0.85 F prime C. Okay, multiplied by AC, which is the area of a concrete. So the trick now is to find what is my AC. The trick now is to find where is my AC, right? So to find it now, I can have 3 different scenarios. 3 scenarios, right? So 3 cases. So case one is if I call this, right? Let me use this blue color so I won't be confused. So if I call it a D, the opening, that would be very confusing. Let me try to use a different number since it's opening. So let's say opening, HOP, right? That's the distance from the top side of concrete to the top side of my opening, right? So if I have first case, A smaller than HOP, right? H opening, right? That means if my AC, this case AC would just equal to 0.8 from MC, that's fine. So equal to A, where this area, and this is with B. Okay, simple as that. But case 2, right? Case 2, I may have a different A. So let me just erase this line up. My A is between HOP, right? And let's just say this is another one. Don't use this color. Blue one is better. Blue one is the fixed distance. So this is H, say OP2. Okay, my A is in between. Okay, so case 2, A is smaller than HOP2 but bigger than HOP1. Right? So what to do? right? What you do now, if I have this case, right? Let me zoom in. Let me zoom in. So essentially, I will have opening right here. I have A in this area, right? This is my AC. So I can simply divide that into two parts. Divide that into two parts, right? So this is HOP1, and this is A minus HOP1. So let's call this area 1, call it area 2. So my AC would equal to HOP1 multiplied by B plus A minus HOP1, which is this much, multiplied by B minus BOP, right? Right, that's the area of 2, area of 1, right? So I can still determine my A using this because ASFY, which is the tension, has to equal to compression. So 0.85 F prime C, and take this whole thing down here, right? Multiply by HOP1 multiplied by B, plus A minus HOP1 multiplied by B minus BOP. I can solve for A and get my compression zone, right? So now here's a question, right? So I solved for A. What about the lever arm? What about the JD? Distance between tension and compression. What about JD? Right? So how to do this is that now you have two pieces, right? You need to find, so let me just move this thing here. You have two pieces, right? You have two areas. So you need to find the center, need to find a geometric center. So find, don't like this very much. Okay, find geometric center of the effective compressive zone. Of the effective compressive zone. Right? How to find that, right? So naturally, to find the center, right, I need a somewhere. I think the center, I'm just making things out, okay? I think the center is somewhere here. Okay, somewhere here. And I will call this Y bar from the top, right, to get the center, right, to get the center. So Y bar, naturally, should equal to area of first multiplied by distance of first piece plus area of the second piece multiplied by the distance from the center of the second piece divided by the total area. Okay, so what is Y1, right? What is Y1? So being that Y1 is from the center right here to the top, right? So I can write Y1 equal to what? A minus HOP1, right? And divided by 2, that's the half of that, right? Plus HOP1. That's the distance, right? And Y2 would equal to simply HOP1 divided by 2. Right? So with this, I can actually solve for my Y bar, right? Bringing all the equation, you have the area already, you have the distance, you can find the centroid, right? So why we have to find the centroid? Because once we find the centroid, JD, which is the distance between tension and compression, equal to D, depth of the section. So this is still D. Okay, depth of the section, right? Minus Y bar. So Mn, which is your moment capacity, equal to ASFY multiplied by D minus Y bar. Right? Pretty simple. Pretty simple. Okay, but this is the moment capacity. Don't forget to check what? Don't forget to check first, epsilon S is bigger than epsilon Y or not, and also phi, strength reduction factor. To check phi, meaning to check if epsilon T is bigger than 0.05 or not. All right, so how to do that? You need C, right? Need C, right? after you determine A, right, which is this fellow here, after you determine A, you can use still C equal to A divided by beta 1, right? To find C, so this is C, right? And equal to beta A divided by beta 1, right? And this is the compressive zone. So you know this is epsilon C equal to 0.003, and you have a depth right here. This is D, and you have all the way down here. This is dt. So how do you find the epsilon s equal to what? D minus C divided by C multiplied by epsilon Cu. Epsilon T equal to dt minus C divided by C multiplied by epsilon Cu. Since that we only have one row, that equal, well, the depth equal to the last layer of the reinforcement. Right? So you find the strain in the steel, you find the strain in the last row of the steel, you check for a epsilon s is bigger than epsilon y or not, then epsilon t is bigger than 0.005 or not. Right? Now this is all for case 2. This is all for case 2. Remember, we have 3 cases, right? We have 3 cases. What are the 3 cases? Case 1, A is smaller than HOP1, right? It's smaller right here. Case 2, in between, so half covering the whole. The case 3 simply is somewhere here, right? Full coverage, full coverage. Now we have talked about this, discussed before, how we're going to solve this, right? So before we use the whole area and subtract the whole like we did in the previous lecture. If you forgot, you can go back and take a look at it. That's how we did for case 3. So the problem is last lecture, we only talked about case 3. We haven't talked about case 1 and case 2. That's why I was asking you guys to hold on the homework. All right, so run your calculation to see how much of the concrete area needed to balance the tension, tension. Decide if it's case 1, case 2, or case 3. If it's case 3, case closed, right? It's very simple. You just do the same thing as we did before in lectures. If it's case 1 or case 2, follow the procedure we talked about today, right? Follow the procedure we talked about today. You have to add one more procedure to find the centroid of the compressive zone. It's a little bit more complicated. Okay. All right. Okay. Any other questions on this? Folks, it's time to speak up because you have homework to do. Are we good on the irregular section? Anything? Quiet, silent? Okay. All right. So let's do this. We'll have another office hour tomorrow, Thursday, right after our lecture hours. And if you have any more questions then, because if you don't, it'll be too late. Monday will be submitting day, right? Monday will be the submission time, okay? So tomorrow, let's go over it if you have any question on the regular section and T-beam section again, okay, on the homework, okay? All right, okay, good deal. So let me close this chapter up, move forward to go back to our shear design, okay? So this is for homework. And let's go back to shear design. So lecture 14, continue for shear. Continue for shear. All right, so what we talked about before, right? Last time, we mainly talk about the sections, right? The sections, right? For the shear resistance, And then we talk about, think about it, phi V N has to be bigger than phi VU, right? Or VU smaller or equal than phi VM. That has 2 parts, that is concrete contribution and steel contribution. Remember? And concrete contribution, we said Vc equal to 2 lambda square root F prime C BWD, right? And V steel, that is another equation based on the stirrups, right? Another equation based on the stirrups, right? So that is AVFYT divided by S, which is spacing, and multiplied by depth D. Okay, so this is pretty much it, right? This is pretty much it for the shear resistance. Okay, but we also said, now this is just the basic concept. For the real practical design, we do something different, right? So we have summarized some table, but I'm going to do this again, right? I'm going to do it summarized again. So first step, right? category. We have the 5 steps and 6 steps listed before, but essentially it coming down to check if Vs required still is smaller than A times square root of F prime C BWD or not. Okay, so if not, if this is not the case, right, you have to increase the section, increase BW or D. Okay, so meaning change section. And you can find this from ACI. You can find this from ACI 22.5.1.2. That's the first thing, right? And the second thing, if this is checked out, the section's okay. So we have to see if, check if VS is smaller than 4 times square root F prime C BWD. If it's smaller than that, right? If so, if it is smaller than that, right, spacing needs to be equal to least of the smallest value of, right? Following as required, right? As required. Remember how we calculate that? Remember how we calculate as required? As required equal to AV FYT divided by VU divided by phi minus VC and multiplied by the depth of D. Okay, multiplied by the depth of D, right? So that's the calculated spacing required. Okay, and check if it's D over 2. Next one, 24 inches. And next one, AVFYT divided by 0.75 square root F prime C BW. Okay, and the last one is AVFYT divided by 50 BW. Okay, so this is that VS still contribution smaller than 4 times square root F prime C BWD. If not the case, okay, you have to change your equation, right? So S equal to least of, right? And things becomes a little bit easier. So S required or D over 4 or 12 inches. 12 inches. Okay. Still, these two carries. So let me just circle it out as a copy. I'm getting a little bit lazy today. Paste right here. Okay. Okay. So this carries. Okay. But most likely, let me say this, it's going to be these two most likely dominants. Okay. Most likely it's going to be these two that dominants. Okay. All right. So you see, it's not hard. It's not hard, right? It's very simple for shear design, right? Apart from the sophisticated thought process, it's not that bad. It's not that bad. Okay. All right. So this is the design equation. This is design equation. But today, the real objective today is not to dabble in the equation right away yet. All right. So the objective, oh man, sorry, color is off. My objective today is to show you critical sections. Location of critical sections. Okay, this is my objective today. Okay, so we know if given the section, we know how to design it. The problem is which section should we design? Right? So for example, given a simply supported beam, okay, and have a uniformly distributed load like this, okay, so I'm gonna have a shear diagram. All right, I know I've been very, very quiet in the past 3 or 4 lectures because a whole lot concept has to convey to you guys speedy. But today I'm gonna slow down a little bit, start asking questions. Okay, so pay attention, guys. If you're sleeping, if you're playing games while watching this, now pay attention. I'm gonna call names now, right? Okay, so my first victim for today, let's see who's on my list. John, JD Crawford.
Yeah, I can hear you.
Hey, how are you doing, buddy?
Great. How are you?
Good. It's good to be isolated at home, hey?
Yes, yes, it is.
All right, good deal. So quick question here. Now I have a simply supported beam, I have a uniform distributed load, right? And I have two locations, right? I have the center span and I have the location at the support. So question is location 1 or 2, which location should we design our shear?
Probably in the middle
Why?
because it's gonna cause like the most bending right there, and the shear it's gonna return to zero on the shear diagram, which I don't know. It just seems like that would be the most vulnerable spot because the supports are located far away.
I see, I see. Right, okay. So I cannot agree with you, unfortunately, on this, JD,
Okay.
because now let's take a look at the shear diagram, right? So you are absolutely right at the second half of the sentence you say, in the middle section, there's no shear, isn't it? Isn't it?
Yeah.
There's no
Yeah.
shear,
So
right, right. So you were right if you were to stick on the 2, okay? Because that's the maximum shear. All right, but good call. Exactly what I want to see. Okay, so don't go in, folks, don't go in right away to see the middle section. We use the middle section for bending moment, but shear is different. Shear is different. All right, so the question, I mean, the answer to the question is we have to design shear from the shear diagram. Okay, have to design based on shear diagram, shear diagram. And the critical section on ends at the support is maximum, is maximum. Okay, but this is not detailed enough. This is not detailed enough. Let me zoom in. Let me zoom in for you, right? So let's take a look at the support here. Let's take a look at the support here. And if this is the bridge, per se, if this is a bridge, right? So what it looks like, actually looks like is something like this. From a side view, that's the top beam, okay, you see on the job side. And I have a column here, okay? I have a column here, okay? And usually I have a rocker. If it's steel, I have a rocker steel plate built like this, okay? I have the ribs on that. And I have a neoprene pads. I have a neoprene pads. What is neoprene pads? They're just layers, rubber and steel, right? Layers, rubber, steel, right? And sit on top of this. So this is called the simply support. This is called the simply support conditions, right? So the question comes now, okay, you say it's at the support critical section, right? You say it's a support critical section, right? So there are various locations, right? I can have right here in the middle line where it lines up, okay? I have right here at the support, okay? So which one would be the critical section, right? Which one would be the critical section, right? Is it here in the middle of the support or is on the edge of the support? Or should I say, if I have a crack, if I have a diagonal crack, since this is where the stress concentration should start, I would have 45-degree angle, 45-degree angle here. And this will be where the diagonal crack ends, right? So I have 1, 2, 3, 3 locations. All right. Wheel of Fortune today. Which one is the critical section? Bryce Kuiper. Bryce.
Hello. Hey.
Hey, how are you doing, buddy?
Good. How are you doing?
Doing well. Sorry I have to keep calling you because I had a master student also Bryce. Sometimes,
Hi.
it's easier. Anywho, so quick question here, right? So I label 3 sections here. Pick one. Which one do you think will be the critical section?
Probably 3.
Why is that?
Since if that would be the end of the crack, it would leave the least amount of space to be the most vulnerable, I guess.
That's exactly right. Wow, you got it. If I have $100 bonus, you'll be getting it today. All right. Thanks a lot, Bryce. That's a really good answer. Thank you. So exactly, right? So this will be my critical section right here. Okay. This will be the critical section right here. Okay, why is that? Because theoretically, okay, your shear diagram will look like something like this. So if this is the end, the maximum shear is probably going to be at the support. Let me use different color. A. Okay, use different color. It's blue. So your maximum shear will probably look like this, right? But we truncate it, right? This is, imagine this is extended shear diagram, and you have the other half go the other way. But imagine we truncate it, okay? So we're gonna use this section right here, which means we're gonna use this value, shear at this point, right? To design for it, So the distance, right? The distance from the edge to the critical section here, this is D. This is D. Okay, so this is the critical section. Okay, so see, it's not that simple. It's not that simple. You have to be able to pick the correct critical section. Matter of fact, right? ACI, let me take the whole thing down a notch. ACI basically says, right? ACI says, you know, folks, this is too much for you, right? Too much for you. I don't want you guys to, you know, get swamped by this detailed information on the job site. You don't have time for it. You don't have time for it, right? So ACI said, I'm going to give you a list of critical sections, list of critical sections. Okay, ACI provided that, and you can find it. You can find it from ACI code. Okay, 9.4.3.2. All right, and let me just write down here, exam, right? You will see this in the exam, right? You'll see this in the exam. You'll see this in the exam, okay? So this is so-called scenario A. Scenario A is simply supported conditions. Okay, now scenario B, when I have cross, right? When I have column beam joint, or beam column joint, right? Beam column joint. Beam column joint. Right? So I have a beam integrated with column like this, and join it here. So this is cut cross section, this is cut cross section, this is cut cross section, right? Where is my critical section? Where is my critical section? Turns out, right, it's 45-degree angle here, 45-degree angle here, and don't draw it the wrong side, right? I had some people drawing the other way, right, which is wrong, okay? So it's distance D away, distance D away. Okay, so this is D, and this is D. What is D? D is the depth of the beam. See, I didn't draw the height, right? It's the depth of the beam, okay? So just make sure you know that depth of beam. Same thing here, right? D is right here, okay? Don't get me wrong, there's a rebar here, so depth of beam. Okay, beam depth. Okay, beam depth, okay? So these are the critical sections. Critical sections. Forgive my calligraphy, my writing is getting worse on this Apple Pencil. Try to improve, okay? Sorry about that. So this is scenario B, okay? Scenario B. Now scenario C, okay? Scenario C, and don't forget the loading, right? This is all for distributed load. Okay, so this is distributed load, and simply supported condition, SS, right? Simply supported condition. This is also distributed load, and beam column joint, right? So let me just showing you here. Okay, and for C, right? I have a beam column joints in a continuous fashion, right? Continuous fashion, right? So if I show the column right here, and this is beam, another column right here, right? And this is beam column and beam column, right? So this is cut, this is cut, this is cut here, cut here, cut here, cut here. So this is again distributed load. So right here, right here, right here, right here, distributed load, right? Be careful which load direction we're shooting at, okay? So the 45-degree angles goes from here, 45-degree angle here. So this is 45, right? 45, and 45 here, 45 here. So critical section here, critical section here, 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 right? So this is D, this is D, and this is D, and this is D. Okay, critical sections right here, critical sections right here. Okay, so for case, yeah, this color is not right. So case D, last case, right? We have a little bit different. We have a little bit, say I have a beam, looks like this, almost like in case A, but I have a lip. I have a lip, right? I have a lip. So this is side view, okay? And also the support, the neural printing pads, all that is here, and this is the support, the column right here. Okay, and now if I have distributed load on the lip, okay, distributed load on the lip, so my critical section will be distance D away from the edge of the support. Okay, so edge of the support, 45. Okay, but in this case, also include this one. So I have two critical section now. Critical section 1, very important, okay? Critical section 2, check both. Okay, one right at the support. Pay attention, it's right at the support, right? At the knee, at the neoprene pads, edge of that. And also the other ones right here. So you have two critical sections, right? So if you don't understand these images, right, I'm gonna flip it on the cross-sectional view, right? What looks like this looks like this. Looks like this. Okay, so this is the section, and the distributed load is sitting on the lip. Okay, and supports right here, and that's the column underneath it. Okay, so this is the cross-sectional view. Okay. All right, so that's the D. Okay, that's the D, or in the code called other cases. In the code called other cases. Okay, now this is called edge load. This is called edge load. All right, I have two critical sections. So most important message is for this case, two critical sections. Okay, now for different scenario, is the beam supported by tensile force case. Beam supported by tensile force. So this is odd. What do you mean by that, right? What do you mean by that, Bob? So what we have seen so far is beam resting on the columns. All these are compression. All these are compression. Okay. In an example, for example, like a balcony, right? For example, like a balcony. I have a beam, okay, but I have another vertical member that is hanging it, right? Hanging the beam, right? So if the beam is subjected to a uniform distributed load, so this is beam, okay? Now the critical section will be right on the joint, okay? Not the 45-degree, okay? Right on the joint. So I need to show you the tensile force, right? So the tension is going this way. So that is called the beam supported by tensile force. Okay, beam supported by the tensile force. Okay, all right. So another case, right? Continue. This is O in D, category D, other cases, right? Other cases. So I'm gonna turn on the 3, right? So I might have a concentrated force as well. So if I have a beam condition like this, right? And then this is the cut, and sorry, this is cut as well. Okay, and if I have a concentrated force right here, okay, so besides the critical section we just described, you need to add one. You need to add one right at the concentrated force, right? Right at the location concentrated force. So this is also the critical section. Okay, so let me write down. So this is concentrated force case. Okay, and number four, right? That is if I have a beam girder scenario. If I have a beam girder scenario, what is beam girder? So both are in bending, both are in bending, but one is a bigger beam. Okay, one is a bigger beam. I'm drawing 3D right now. Okay, so this is my girder. Okay, and the other one is a smaller beam. The other one is smaller beam, so something like this. Okay, so something like this. So two beams across, okay, and this is the beam. That is the girder. Okay, so this is called beam girder intersection, right? Beam girder intersection. That means I have to consider a critical section. Let me shade it for you. Right here at the joint. Right here at the joint, at the junction. Okay. All right. Okay. So these are the critical sections you have to consider during the shear design. Okay. And I cannot stress enough. Remember this. I cannot stress enough. You need to remember this. If you have time before the exam, right, put it on the creep sheet. Put on the creep sheet. Okay. You need this. Even for your future design, okay? Just you know where the critical section is at, because you are going to pick the shear force at these critical sections for design, okay? Let me say this again, okay? You're going to pick up the shear force at these critical sections for design. Why am I saying this again? Because the shear force at these critical sections may not be the maximum shear force in the member. Okay, you see, it may not be the maximum shear force in the member, but you pick it at this critical section nevertheless. Okay, question?
So for point 3, or for the D section 3, right? Would we have to do one at the edge of the support right there?
This is like L shape, like connection. You don't have to do right here anymore since there's no distributed load. But if you have distributed load, right? If you have distributed load, right? What you do is you pick the critical section and the concentrated force, and you also, anyway, you also add one for the 45-degree distance D.
Got it. Thank you.
Right. It's more like a combined scenario. So what this case is trying to tell you that whenever you have a concentrated force, do a section right there. Just be safe. Got it?
Yep. Thank you.
Great deal. Okay. All right. Okay. So this is a good time to stop. Any other questions on this, on the critical section? Well, if you have, welcome to stay behind. If you don't, I will see you tomorrow, okay? Start working on the homework, please. Start working on the homework, please, okay? I know you haven't started. A lot of you haven't. So please start right now, okay? Because you have questions. You have questions. Homework 6 is pretty serious, okay? So ask these questions tomorrow during our lecture time, and I can stay behind and answer any questions, okay? All right, I'm going to stop recording. And if you have any question, welcome to stay behind.